Okay, so now we will solve question 5. So you can see we already solved two other problems, and those problems it was a little bit different. So for that question we use different techniques, but this is a little bit different problem. So let's read the problem at first. An incompressible viscous fluid enters a horizontal circular pipe at the inlet section 1. So this is our inlet section with uniform velocity. So initially the velocity it was uniform. You can see this arrow, so they are in the same, the length is the same for all of these arrows. So this arrow actually it is telling you the magnitude and the direction as well. So it is uniform velocity u0, and you can see this too. Actually this is the, let's say that some distance downstream, that means section 2, the velocity becomes parabolic. So you see the profile, initially it was uniform and now it becomes parabolic. So you already know this parabolic means the flow is fully developed here. So which means it was the initial velocity, and for when it is fully developed flow, the velocity magnitude it will be maximum at the center. Okay, so this is the center of this pipe. So you can see the velocity is maximum. So if you see the velocity profile this way, it was increasing, so it creates the left boundary layer here, and the other velocity boundary layer forms this way, and they merge at this position. So this is the center line. You can see this r, we said this is the radial distance, and u center, this is the velocity along the center line, and r is the pipe radius. Okay, so we need to obtain an expression for drag force by the following fluid on the pipe wall over the line 1 and 2 in terms of pressure at section 1 and section 2. So the density is given rho, pressure, pipe radius is r, and the inlet velocity is u0. So you can see from this problem, initially it was uniform velocity at section 1. At section 2 it becomes parabolic or fully developed flow, and now we know the radius, we know the radial distance and the velocity along the center line. We need to obtain an expression, so an expression for the drag force. So we're going to obtain the expression for the drag force for the length 1 and 2. So now we will start with the solution. Okay, so if you see here, this is this schematic of this total system. We say this is the section 1, this is section 2. This is the free stream velocity. So you already know we have the velocity here, so definitely we have, so let's say the pressure P1 is here. So this is the pressure directions, and we already discussed, when we saw the first two problems, and then we said the pressure it is, always acts through the normal direction through the area. So this is the area here. This is, let's say this is the inlet section. If you can remember the mass conservation principle or the equation of continuity, so we know from the mass conservation principle, the flow through one section it will be equal to the other section, the mass flow rate. So let's say here the mass flow is the velocity into the area. Okay, before going to that section, let's describe a little bit about how this schematic is working here. So we say the pressure P1 here for this section 1, the free stream velocity is u0. So you say this is the uniform velocity for pipe flow, so you don't need to say free stream. This is the section where the flow becomes parabolic, and this is the u center. Let's say we have the coordinates, so this is the x coordinates and this is the y coordinates. So this is the x directions. According to the Newton's third law of motion, so the force we have, the force, two different forces are acting here. So one is the fluid, which is just putting some force on pipe, and the pipe, one fluid. So the fx, the positive, this is the positive directions. So you see the fluid is going this way, so the force is this directions. So there should be an opposite force fx in these opposite directions by the pipe, one fluid. Okay, so you see the fx by pipe, one fluid. So what is said according to the Newton's third law? Yeah, so every force has an equal and opposite force. So if you hit me, I will hit you. That's something like that. So the fluid is putting some heat on pipe, so pipe will also just put some opposite force. So this force is going to the opposite directions. Here the velocity, we say this is the u. If we consider this a small section, let's say this is the dA, very small section, the differential area. So when we do a very small section, so the area is 2 pi r, and this is dr, because we're taking very small section, so the area of this small section is 2 pi r dr. Flow is become parabolic here. So if we want to calculate the mass flow rate in this section, according to the mass conservation principle, the total flow here, it will be equal here. So then we can say the mass at this section is the velocity and the area. Velocity is u0 and area is a1. So this is for section 1. It should be equal to the mass at section 2. But at section 2 we took very small section, and this is the area of that section. This is dA, and what is the velocity? Velocity is u. So if we want to get the mass for the whole section, we need to integrate. So integrate this, and this is u dot dA. This is the velocity and this is the area. Now look, u0 is the velocity it is given, and the area for this section, it is pi capital R square, because we know R is the pipe radius. But here the flow becomes fully developed, that means the parabolic, and you see the velocity there is u equal u center 1 minus small r by capital R square. So that means we need to replace this u by using these expressions, like u 1 minus small r square and capital R square, and the area is 2 pi r dr, right? So this is the area. So we put this area here, and this velocity we got from the parabolic profile. So now the thing is, we are doing these integrations because we want to calculate the mass for this section, but initially it is for this small section. So if you want to get for this whole section, what you need to do is you need to put some limit. So the upper limit is the pipe radius, and definitely this is the center. So you can say the r, the small r, it is equal 0, and this is the lower limit is 0, upper limit is r. So this is actually the mass conservation principle for this problem at section A and section 1 and section 2. So once we know this, we need to calculate an expression. So let's see. So now an important the theory is when the velocity will be fully developed. So what we said, this is the fully developed profile, velocity profile, and I said initially that the velocity here, it will be maximum. So according to the theory, when the velocity will be parabolic or fully developed, the velocity at the center, it will be twice of the initial velocity. That means this u, it will be just 2 times of this initial free stream velocity. So that's actually the theory. If it satisfied this condition, then we can only say the profile is parabolic or fully developed. So with the parabolic velocity profile, the velocity at the center u, it is 2 times of this velocity. That means u equal to u0. Right, so we need to use that. And now if we use the control value between this section 1 and this section 2, So then you know the sum of the the force, the net force along the x direction. So if we consider along this x directions, so the net force along the x direction, it will be the sum of the momentum net, it will be equal to the net momentum that we solved throughout the problems initially. So what sort of forces we have along the x-axis? So I previously said we have one force fx, it is by pipe on plate, it is going to the opposite direction, so that's why you can say it will be negative fx by pipe on plate. We have the other force, see, we have pressure P1 A1 here, so that means that we have force P on A1, so it is going to the opposite direction, it is going to the positive x-axis, so this should be positive P on A1. If the pressure P1 is acting this way, so for here pressure P2, its direction should be opposite, because you know the ideal gas theories. So we have the pressure P1 in this direction, so P2 it should be this way, because from every side there will be a similar amount of pressure. So in this section we have the pressure, if I use some other color, so let's say in this section it will be P2 A2, the pressure, and it is going to the opposite direction, see this opposite direction, so it should be negative P2 A2. So that's the total force we have. The fx, this is the negative force, it is going to the opposite directions. This P on A1, this is in the positive directions, and this P2 A2, it is the opposite directions. It will be equal to the the momentum for this section 1 and 2, that's the net momentum. You know the formula, rho px v dot dA. So this is the velocity along x-axis, this is the dot products. So now we will solve this expression, and then we will get an expressions for that actually what we are looking for. Okay, so now you see for section 1 the momentum, for section 1 we can write it is the rho, the density by x1. X1 is for section 1 and this is v on A1, because we know the area for section 1 is, you see here the area for section 1 is A1, but for section 2 this is the differential area we used. So what I said, this is the Vx1, the velocity for section 1, V1, and the area A1. But for section 2, definitely we need to do some integration. So this is the rho, the velocity is u given. You just look here, the velocity is u given, and the area is dA. So this is, you see the u and u dot dA. So I told you earlier that okay, for especially for this types of problem, when you will calculate the momentum, it is the final momentum minus the initial momentum. So definitely this section 2, this is the final momentum and this is the initial momentum. So the difference between final and the initial momentum, I told you we can explain it different ways based on the area. So depending on the directions, when we put the dot product, then we'll get this velocity negative. But okay, I'm trying to follow the same style, so I say the final momentum minus the initial momentum. So okay, the velocity along the expression, this is u naught, alright, and this is the u naught and phi r square. So total it will calculate the momentum difference, the final momentum minus the initial momentum. So as I said, we can explain it different ways. I'm trying to make it simple. So I said okay, the initial momentum, this is, we'll subtract that with the final momentum, so that it should be negative. So this is the negative sign here. Now this is the rho. We want to calculate the moment for for the whole domain, for that whole section. This is the the differential section. So put that lower limit and the upper limit 0 to r. This u equal, we know u center into 1 minus small r capital R. Then it is u again u into 1 minus r square small r square capital R square into 2 dA equal to pi r dr. So this is actually u. This is actually u. Right. So now it should be negative, rho pi u naught square r square. We will get some common terms here. This is constant 2 pi rho and the u r square center. So if we just, this is the common term in between two. If we multiply these two velocity terms, then it will be r square over 2 to r4 for r square r6 plus 6 r4. I believe this is very simple calculation, so you need to just multiply this one and this one. So we will get something like that. And definitely, it is not only the multiplication, so you need to do the integrations here. So if you simplify it, after the just multiply this one at first, then integrate it, and you will get this term. And I believe we solved some similar problems, and you already know how to do these simple integrations. And just put this limit, and if you simplify this, then we will get these expressions: 1/3 pi rho capital R square and u naught square. So once we have this, what we can do, we can just have a look here. So we know the negative fx, this is the bipole one fluid, and this p1 a1 p2 a2 equal this. So what we can do, we can do some simple simplifications, like what we actually need this fx, the force. So we can write it as fx equal the p on a1 minus p2 a2, and minus this value 1/3 pi rho capital R square u naught square. So actually the area is pi r square, so then it will be the area at a1, area at a2, this is the same. You see the area a1 a2, actually we know the pipe radius, so this is same. So a1 a2, it should be pi r square. So if we just if we consider this is the common term, so this is p1 minus p2 pi r square, and this is we just calculated. So this is actually the fx bifluid on pipe. So that's the expression we just calculated, and this is actually the what we are looking for.